Good morning, dear students. Last class, you studied about Newton's third law of motion and its real life applications. Today, my class, I would like to present to you three topics. First one, law of conservation of momentum and its deduction from Newton's third law of motion. Second, activities to demonstrate Newton's third law of motion or law of conservation of momentum. And third one is related numerical. The first topic is the law of conservation of momentum and how can it deduce from Newton's third law of motion. What is law of conservation of momentum? In physics, there are so many laws that it becomes difficult to memorize all of them. You all have been familiar from different types of laws like laws of motion, laws of inertia, and the list goes on. We can even interpret many laws from its name only, like law of motion is related to motion, law of attraction is related to attraction. So now you can guess from what the law of conservation of momentum is related to. But it is not enough to know only that is related to which thing. So let's head towards the real phenomenon of law of conservation of momentum. The principle of conservation of momentum states that if two objects collide, then the total momentum before and after the collision will be same if there is no external force acting on the colliding objects. Conservation of linear momentum formula mathematically express the momentum of the system remains constant when the net external force acted on them is equal to 0. That is, initial momentum is equal to final momentum. Law of conservation of momentum can be defined as when two objects are colliding in an isolated system, then the total momentum of two objects before the collision is equal to total momentum of these two objects after the collision. So we can simply say that if two objects are colliding in an isolated system, the total momentum before and after the collision is equal. Here I am mentioning the isolated system again and again. What is meant by isolated system? The isolated system is that system that does not interact with the surrounding. That is, its total mass and energy remain same. So there will be no external force or energy which will change the result for momentum. Are you thinking about how does Newton's third law of motion relate to law of conservation of momentum? You know that when two objects are interacted with each other, they exert an equal and opposite forces on each other. This is Newton's third law of motion. This also implies that these same forces act on these two different objects for the same amount of time. In earlier class you learned Newton expressed his second law of motion as the net force acting on something equals the rate of change in momentum of the thing. If two interacting objects necessarily experience opposite forces that last the same amount of time, they will also experience opposite change in their momenta. That is, this is in accordance with Newton's second law of motion, as rate of change of momentum of an object gives the magnitude of the force acted on it. So whenever there is change in momenta of two interacting bodies by their interacting forces, that is action reaction forces, there is no overall change in momentum or net magnitude of change of their momenta will be equal to 0, because change in momenta of these interacting objects are equal and opposite. Here two same magnitudes, but one is positive and another is negative. When they are added to get zero magnitude. Therefore, you can understand that Newton's third law is used to derive law of conservation of momentum, or it is useful to verify law of conservation of momentum. Next topic, you are going to study how can deduce law of conservation of momentum from Newton's third law of motion. Suppose two objects, here we have considered two balls A and B of masses MA and MB are traveling in the same direction along a straight line at different velocities UA and UB respectively. There are no other external unbalanced forces acting on them. Let UA is greater than UB and the two balls collide with each other as shown in figure. During their collision, which lasts for a time t seconds, the ball A exerts a force FAB on the ball B, and the ball B exerts a force FBA on the ball A. Suppose VA and VB are the velocities of these two balls A and B after their collision, respectively. Then the momentum of the ball A before collision is MAUA and its final momentum is MAVA. By applying Newton's second law of motion, the rate of change of momentum during the collision for A will be FAB is equal to MA into VA minus UA divided by T. Consider the ball B, its initial momentum is MBUB and its final momentum is MBVB. Again, on applying the Newton's second law of motion, the rate of change of momentum of B will be FBA is equal to MB into VB minus UB divided by T. According to Newton's third law of motion, the force FAB exerted by the ball A on the ball B and the force FBA exerted by the ball B on the ball A must be equal and opposite to each other. That is, action is equal to minus reaction. Action FAB is equal to minus of reaction FBA. Therefore, MA into VA minus UA divided by T is equal to minus of MB into VB minus UB divided by T. By cancelling T's in both sides of above expression and rearranging the terms, we get MAUA plus MBUB is equal to MAVA plus MBVB. Therefore, MAUA plus MBUB is the total momentum of these two balls A and B before collision, and MAVA plus MBVB is their total momentum after collision. Hence, we have proved the law of conservation of momentum. Now, let us discuss on two activities to demonstrate Newton's third law of motion. Activity number 1. For doing this first activity, two student scales are required. Tie one end of a string to a rigid support on a wall in room. Put the other end of the string through a straw. Then pull the string tight and tie it to another support in the room. Blow up the balloon and pinch the end of the balloon to keep the air inside. Tie its neck with thread. This arrangement is made as shown in figure. Tape the balloon to the straw so that the opening of the balloon is horizontal with the ground. While holding the balloon opening closed, one student should pull the balloon all the way back to the end of the string so that the balloon's opening is against one support. It is the starting line. Have another student use the marker to draw a finish line near the other end of the string. Let go of the balloon by removing the thread tied on the neck and watch it to move along the string. What can you observe? You observe the direction in which the straw or balloon moves. it is seen that balloon along with the straw moves from left to right position on the string, and the expelling of the air out of the balloon is opposite to the direction of motion of the balloon. What can you understand from it? Surely it shows action reaction forces. The removal of the air from the balloon is action, and the air exerts an equal and opposite force on the balloon so that balloon can move along with the string. This is reaction. This activity shows Newton's third law of motion. Activity number 2. Here we have to take a test tube of good quality glass material and put a small amount of water in it. Place a stop cork at the mouth of it. Now suspend the test tube horizontally by two strings or wires as shown in figure. Heat the test tube with a Bunsen burner until water vaporizes and the cork blows out. You observe that the test tube recoils in the direction opposite to the direction of motion of the cork. And also observe the difference in the velocity the cork appears to have and that of the recoiling the test tube. Here the cork is thrown away with a larger velocity than recoiling velocity of the test tube. Why? Because the mass of the test tube is more than the cork. It is found to be final momentum of the cork is equal and opposite to the final momentum of the test tube. So we can say that the total momentum of these two objects just before and after the event is always conserved. That is, it will be equal to 0. You know that initially these objects are at rest, so their initial momenta will be always equal to 0. What is action and what is reaction here? When vaporized water acts against the cork is thrown away. This is action. But the cork exerts equal and opposite force to the vapor so that it could force to move the test tube in backward direction of the motion of the cork. It is reaction. From these two activities, it is also clear that the total momentum of these two objects which are interacted with each other is unchanged. That is, it is conserved. Hence, we can say that the two activities described before also demonstrate the law of conservation of momentum. Now, let me discuss on the way to derive the recoil velocity of a gun on its fire. Consider a system consisted of a gun and a bullet. The initial momentum of the system is equal to 0, as both the gun and the bullet are at rest initially. Final momentum of the system is equal to final momentum of the gun plus final momentum of the bullet, which is equal to capital letter M into capital letter V plus small letter m into small letter v, where capital letter V be the recoil velocity of the gun and small letter v be the final velocity of the bullet. By applying the law of conservation of linear momentum, the initial momentum of the system is equal to final momentum of the system, where 0 is equal to capital letter M into capital letter V plus small letter m into small letter v, which implies capital letter V is equal to minus of small letter m into small letter v divided by capital letter M. Here the negative sign indicates that the direction of velocity of the gun is opposite to the direction of velocity of the bullet. Do you know about principle of working of a rocket? Rocket works on the principle of law of conservation of momentum. The gas to be ejected from the nozzle of the rocket exerts force on the rocket, and no other external force works on the rocket to shoot it upwards. So the rocket gains momentum. By applying Newton's third law of motion, rocket pushes the burnt fuel gas with equal force but in its opposite direction. So the gas gains momentum and moves in opposite direction to the rocket. Suppose the gas is ejected with velocity small letter v and mass of the fuel gas is denoted by small letter m. Mass of the rocket is denoted by capital letter M and velocity of the rocket is denoted by capital letter V. Now, according to law of conservation of momentum, initial momentum of the system is equal to final momentum of the system. Initial momentum of the rocket is equal to mass into its initial velocity. As the rocket is rest initially, so its initial velocity is equal to 0. Then initial momentum is equal to capital letter M into 0 is equal to 0. Let me think about initial momentum of the fuel. Fuel is also at a rest position initially. Its initial momentum is equal to mass of the fuel into its initial velocity is equal to small letter m into 0 is equal to 0. Then initial momentum of the system is equal to sum of initial momentum of the rocket plus initial momentum of the fuel, that will be equal to 0. Now final momentum of the rocket is equal to mass of the rocket into its final velocity is equal to capital letter M into capital letter V. Final momentum of the fuel is equal to mass of the fuel into final velocity of the burnt gas. It will be equal to small letter m into small letter v. Now, final momentum of the system is equal to sum of final momentum of the rocket plus final momentum of the fuel. That will be equal to capital letter M into capital letter V plus small letter m into small letter v. Now applying the law of conservation of momentum, 0 is equal to capital letter M into capital letter V plus small letter m into small letter v. So capital letter M into capital letter V is equal to minus of small letter m into small letter v. Then capital letter V is equal to minus of small letter m into small letter v divided by capital letter M. The negative sign indicates that the rocket moves in opposite direction to the motion of the burnt fuel gas. Let me go to the numerical part. First question is, from a rifle of mass 5 kg, a bullet of mass 50 gram is fired with an initial velocity of 50 meter per second. Calculate the initial recoil velocity of the rifle. We know the law of conservation of momentum. By applying the law of conservation of momentum, sum of their initial momenta is equal to sum of their final momenta. Here, the mass of the rifle, capital letter M, is equal to 5 kg. Mass of the bullet, M, is equal to 50 gram. That is equal to 0.05 kg. Initial velocity of the bullet U is equal to 50 meter per second. We have to find initial recoil velocity of the rifle. It is represented by capital letter U. And also we know that their final velocities will be equal to 0. The final velocity of the bullet V is equal to 0 and final velocity of the rifle capital letter V also will be equal to 0. By using the law of conservation of momentum, M into U plus capital letter M into capital letter U is equal to M into V plus capital letter M into capital letter V, that is equal to 0.05 kg into 50 meter per second plus 5 kg into U is equal to 0.05 kg into 0 plus capital letter M into 0, that will be equal to 0. Here 5u is equal to minus 0.05 into 50. Then u is equal to minus 0.05 meter per second. Here the negative sign indicates that the velocity of the rifle is just opposite to the bullet. Second question is, a bullet of mass 20 gram is horizontally fired with a velocity 150 meter per second from a pistol of mass 2 kg. What is the recoil velocity of the pistol? Given that the mass of the bullet m1 is equal to 20 gram, which is converted into kilogram, that will be equal to 0.02 kg. The mass of the pistol m2 is equal to 2 kg. And the final velocity of the bullet v1 is equal to plus 150 meter per second. Here the direction of the bullet is taken from left to right, which is the positive by the convention. Let v2 be the recoil velocity of the pistol. According to law of conservation of momentum, total momentum of the pistol and the bullet before the firing will be equal to the total momentum of the pistol and the bullet after the firing. That is, m1 u1 plus m2 u2 is equal to m1 v1 plus m2 v2. First we have to find the total momentum of the pistol and the bullet before the firing. That is m1 u1 plus m2 u2, which is equal to 0.02 kg into 0 meter per second plus 2 kg into 0 meter per second. That is equal to 0 kilogram meter per second. Next we have to find the total momentum of the pistol and the bullet after the firing. That is equal to m1 v1 plus m2 v2 is equal to 0.02 kg into plus 150 meter per second plus 2 kg into v2 meter per second is equal to 3 plus 2 v2 kilogram meter per second. By applying the law of conservation of momentum, we get 3 plus 2v2 is equal to 0. Then 2v2 is equal to minus 3. So v2 is equal to minus 3 by 2 is equal to minus 1.5 meter per second. Here negative sign indicates that the direction in which the pistol would recoil is opposite to that of bullet, that is right to left. And third question is, two objects each of mass 1.5 kg are moving in the same straight line but in opposite directions. The velocity of each object is 2.5 meter per second before the collision, during which they stick together. What will be the velocity of the combined object after collision? Here given that mass of one object m1 is equal to 1.5 kg, mass of other object m2 is equal to 1.5 kg. Velocity of mass m1 before the collision v1 is equal to 2.5 meter per second, and velocity of mass m2 v2 is equal to minus 2.5 meter per second. Negative sign indicates that mass m2 is moving in an opposite direction. After the collision, two objects stick together. Then the total mass of the combined object will be m1 plus m2. Let v be the velocity of the combined objects. According to the law of conservation of momentum, total momentum before their collision is equal to total momentum after their collision. That is, m1 v1 plus m2 v2 is equal to m1 plus m2 into v, which is equal to 1.5 into 2.5 plus 1.5 into minus 2.5 is equal to 1.5 plus 1.5 into v, which is equal to 3v. So v is equal to 0. Hence, the velocity of the combined object after the collision is equal to 0 meter per second. Today's homework questions are given in this slide. Please you have to practice by today itself. Dear students, I hope all of you are fine. You are the safe stay with your own family. By today's class, the chapter Force and Laws of Motion has finished. So I request all of you to revise the chapter again and have the self-assessment test. Okay, thank you. Have a nice day.